go back to this question. This is a joint work we did with Rob Ahrens, Mike Allen, and Carl Walters, and we particularly wanted to ask how size limit variations could work in Pike. And we actually, the study is not just focused on Pike, we also looked more generally at this question, but we informed the model at the end with Pike life history, in fact, Baltic Pike life history. So in generally, we have trade-offs in fisheries, like in the world more generally. Typically, this is how the yield curve develops, associated also with the abundance of fish. And there is this classical trade-off that if you manage a fishery for maximum biomass yield, you typically have a lower abundance and a smaller size structure. And if you are now an angler, you will often enjoy high catch rates, as Dieter showed. 3 pike per day is pretty good. If you go from 0 to 3, you get lots of utility and you enjoy big fish. So if you're an angler, perhaps you want to have a lower fishing mortality rate. So a manager would have a trade-off how to design regulations so to meet perhaps different fishing groups in the same fishery. Now, if you look back in literature, we have, in terms of the size limits as one way to navigate that trade-off, we have a dominance of a minimum length limit as kind of the solution to the problem if you don't have quotas. So essentially, you manage a fishery based on size selectivity only, and then self-regulation of the effort. And the idea for the minimum length limit came up through classical yield per recruit models in the early 50s. There was a few papers there, including one in Nature, that basically said it's a good idea to let fish grow until they get the maximum growth potential, which is often at that age class where the biomass of that cohort is maximum. This is often called H-opt or L-opt, and this L-opt is larger typically than maturation length. And if you let the fish spawn at least once before that, so you make that threshold large enough, you will have 2 benefits. First, you maximize biomass yield, and secondly, you maintain the stock because you have let fish spawn at least once. And this should actually assume in the broader patterns that drive population dynamics, which are growth rate, reproduction, natural mortality, and fishing mortality, that you cross off reproduction being limited. If you let the fish grow long enough, they spawn at least once, that should take care of it. And that was the justification for the minimum length limit as a standard tool, especially in fisheries where you don't have quotas. Now, you zoom lots of years further, and I would say since the early 2000s, mid 2000s, and a next type of literature has emerged. Wait a second, if you just manage with a minimum length limit, you certainly promote aggressive culling of large fish. So that's a fish that is of no big use in such theory. And there are many people now that say that this might be wrong. There might be an undervaluation of the bigger fish and their presence, especially for recruitment dynamics. And there might be some value to protect them more. This research has seen a spike more recently, for example, through Barnesh's paper. I think Jan Doyle mentioned it, where he looked at over 300 fish, marine fish, in terms of the relationship between mass, the measure of length, and the fecundity of fish. And typically you assume that this is a linear relationship, but they showed that there's actually an exponential relationship because the exponent is significantly larger than 1. So these larger fish might have even more fecundity than are traditionally assumed in most classical fisheries models. And then there are other benefits of large fish, for example, egg quality benefits of experience during spawning, as well as the social benefits that those create that might demand more protection. So with that in mind, our studies asked 4 very basic questions. We developed a fish population model and informed it by a range of uncertainties, for example, different types of stock recruitments and different degrees of density and size dependency. And we wanted to ask for that model which optimal regulation that model would predict that meets each, either individual fisheries objectives, biomass yield, which is the classical one, but anglers would perhaps like numerical yield more, or maintaining a high catch rate, or maintaining a high catch rate of trophy fish. Second question, which size-based regulation would create a good compromise where you don't give up on any of those objectives, but you achieve a pretty good outcome. So you achieve good compromise among 3 or 4 objectives at the same time. And then we ask, how does this result, how robust is this to variation in population ecology? And fourthly, what is the systematic impact of size-dependent maternal effects, both on the egg number, which is the hyperallometry idea, but also on the egg quality, which is the second component of a maternal effect. Does the presence of size-dependent maternal effect change the optimal regulations? To study this, we use classical age and size structured fish population models. It's single species fish population models that runs through the age classes. It's informed by either a Bevan and Holt or a Ricker type stock recruitment. I show you in a minute. We can add size-dependent fecundity relationships that are hyperallometric or not. And we added either yes or no, the presence of size-dependent egg quality benefits. We run this model to equilibrium and do an optimization routine to ask which type of size limit, a minimum length limit or a combination with a maximum on top, which creates a harvest lot, would produce an optimization for a single objective in this color coding here, or a compromise among those objectives. We used very standard mathematical representations here, for example, Bevan and Holt type stock recruitment or Ricker type stock recruitment, which some say is more likely for Pike, where you have through cannibalism, overcompensation at high stock sizes. And we had size-dependent natural mortality rates of different degrees. We have Fombert-Talamfi growth rate. And then we have several scenarios for the absence or presence of hyperallometry, as well as here, the absence of any benefit of size of fish on the egg quality or a major benefit. So that's the scenarios we explored, and then asked the question of which regulation is optimal. So let's jump to the results. This will spend a little time on this graph, and the others will then become easier. You see here a plane, and this is the size limit that is predicted to be optimal to achieve, in this case, optimal biomass production of your stock, either in the presence of a Bevan and Holt type stock recruitment, or in the presence of a Ricker type stock recruitment, which is more likely for Pike. And if you only see one plane, it says a minimum length limit is predicted to meet that objective best. And then on the X and Y axis, you see different assumptions about how strong the population responds with density dependent growth. Either it does not respond here in the origin, or the Pike grow much better as they get exploited and the density goes down. And on the Y here is the degree of size-dependent mortality. The classical yield per recruit theory assumes there is no size-dependent mortality. That would be the origin here. Or you have lots of size-dependent mortality. Young fish die much more than larger fish. So what you see here, independent of the stock recruitment curve, and independent of the degree of density dependence and size dependence, in all cases, a minimum length limit is considered optimal. The model says you should let the fish grow to a certain size, defined by a length over length of infinity, and then harvest them aggressively. You can even go down with the size limit, the more the compensatory potential of a stock is, meaning the higher the density dependence in growth response is, and the higher the size-dependent mortality, the more resilient the stock is, so you can fish them harder, meaning at smaller length when they enter the fishery. But this really shows the classical finding in the textbooks. If you are only interested in biomass yield, use a minimum length limit. This changes if you now optimize for numbers yield. So you want to get as many individual pike as possible from your stock. This, I would argue, is better for an angler case where you want to distribute individual fish among anglers. And now the situation changes. You see a second plane coming in, and the model says under these conditions, even in the absence of hyperallometry and even in the absence of size-dependent maternal effects, so just with the classical assumption of a linear increase in fecundity with length, a harvest slot becomes optimal. And this harvest slot widens as the density dependence goes up and the size dependency goes up. Again, because a fish stock that has higher compensatory potential is actually more resilient, and therefore you can fish it harder. But if you would just change the objective from biomass yield to numerical yield, the model would predict you should actually manage this with a harvest slot. If you then go even to other objectives that particularly recreational fisheries like, for example, catch rate, the situation becomes even more dramatic. In this case, if you would like to maximize the catch rate of pike, you would manage with a very narrow harvest slot if there's lots of density dependent growth, or you would not harvest at all, which means the upper and the lower are on top of each other if the fish don't show any density dependence. And this is because with a lot of density dependence, if the stock is unexploited, the growth rate declines. So in fact, some level of exploitation might be good. And pike shows density dependence and size dependency. So a harvest slot would optimize catch rate. It would not be total catch and release policy that would maximize the catch rates. And the very same is also the case if you sorry, I mentioned here a lot about catch rate, but this is the same pattern as managing trophies. So this is for the trophy objective. And again, harvest slots are considered optimal, but not, and this is very important, total catch and release policies. Some level of exploitation is important to facilitate the growth rate, but it's not a minimum length limit that would optimize this. If you now ask the question of compromises between biomass yield, numerical yield, catch rates, and catch rate of trophy fish, our simulations suggest in all cases, whenever you have one additional objective to a biomass yield, you should better manage with a harvest slot than with the classical minimum length. This was a very robust result in all cases. For a compromised objective, go for a harvest slot. What does this do? It basically means that you are moving the optimal fishing mortality rate from those that just looks at biomass yield to something else, left of that curve, which also maintains a higher abundance, which benefits catch rate, but has some form of exploitation to facilitate fast growth, which then also creates trophy fish. So all of what I just mentioned was for a certain fishing mortality rate. Of course, we also can ask the question, what happens if you modify that fishing mortality rate? So you can have stocks, for example, where there are limited anglers or limited fishers, where there's limited fishing mortality rate, or you can have very aggressive situations. And this is shown here with the x-axis being the degree of fishing pressure that exists on a given system. And then you have the four objectives here. And whenever you see a bottom line here, a solid line, it says a minimum length limit is optimal across the gradient of fishing mortality rate. And when the broken line comes in, you see that a harvest slot is considered optimal. And for example, for the biomass yield, when you assume that a fecundity of fish is linear with mass, it's always a minimum length limit. And the more fishing you have, the minimum length limit should increase. By contrast, for numbers yield, you would also have a minimum length limit, but after a certain fishing pressure, actually a harvest slot becomes optimal. If you want to reach trophy fish, it's always a harvest slot. And in a compromise, unless the fishing mortality is really small, you will always get a harvest slot being optimal. Now, this red curve is where the current Rügen fishery basically lies. So we would argue, based on our model, that in our fishery, which is currently a minimum length-based fishery, a harvest slot probably creates a better compromise among those multiple objectives, and we have a fishery where we both have commercial and recreational interests. Now, finally, how would these results change if there would be size-dependent fecundity effects? So if there would be maternal effects in the pike stock, and Jan Droll showed that there is evidence for hyperallometry with an exponent of 1.1 in the pike fishery. This is the final result I'm going to show you. This is for simulation runs where you have that presence of hyperallometry, and you see one big change. And this big change, if you look on the top left, relates to what is expected to be optimal for biomass yield production. And you see that hyperallometry makes even that objective change from a minimum length limit to a harvest slot, particularly at high fishing mortality rates. I should say that our models suggest this to be the case at an exponent of 1.4 or larger. the pike stock in Rügen has an exponent of 1.1. So we would argue that this is of no relevance for the pike stock. So we would not assume that this is really relevant for the current stock, but it might be relevant for other species out there. And it would actually then mean that the textbooks have to be rewritten, because it would say, even if you are managing for biomass yield, if there is lots of hyperallometry, then a harvest lot should be the default situation. So if you summarize this, management is difficult because you have to deal with lots of often competing objectives. So it really depends your suggestion on what your objectives are. If the fisheries objective is to maximize biomass yield, which you would do in a commercial fishery, of course, then a minimum length limit in many cases is just fine and the best objective, the best regulation. If you modify that objectives to the numbers of fish that are taken, and that should be maximal, our model suggests that harvest lot is a better tool. And whenever you have biomass yield plus at least one of those other objectives I mentioned, our model suggests a harvest lot will always be the best tool. If you think about conservation, on the other hand, where perhaps fisheries doesn't matter, you simply want to conserve the stock. If you're only interested in avoiding recruitment collapse, anything goes that has a large enough size limit where the fish can spawn at least once or twice. So it really doesn't matter whether it's a minimum or a harvest slot. If you want to have a more natural age structure, however, harvest slot would produce that better than a minimum length. And perhaps we have not accounted for all mechanisms in our study. And if you want to have increased resiliency and a precautionary approach, perhaps a harvest slot is a better situation. If you want to achieve higher standing biomass, again, a harvest slot simply protects more as long as the fish are able to grow through, which depends on the local fishing pressure, of course. So final slide, how would anglers perceive this? We have done, as Dieter showed, a big survey here, and we have a basic finding that at least in our area, the majority of people in general prefer higher constraints, and there's a very high fraction of people, over 80%, that consider a harvest slot to be something that should be introduced from the perspective of the anglers, at least in the local fishery. We are currently running a survey with the commercial fishermen, and then we can see how these different groups align or not on that question. If you're interested in the details of the study, this has been published already in the journal Fish and Fisheries. It's an open access journal. And I want to thank the funders and my collaborators that helped me immensely to put this together. Thank you very much.